Let us continue hybridization. For hybridization, we will take a molecule beryllium chloride we are taking. In this central atom is beryllium, atomic number is 4, electronic configuration is helium 2s2 2p0. Now 2s contains 1 orbital, 2p contains 3 orbitals in the valence shell. Now beryllium chloride structure as per VSEPR theory we are seeing structure is so and so. Beryllium chloride structure is so and so. Beryllium valence shell is having 2 bonds. Therefore, from beryllium valence shell, 2 atomic orbitals undergo intermixing to give hybrid orbitals. 2 atomic orbitals in the sense we have to start from least energy in the valence shell. In this valence shell, least energy is 2s. 2s contains 1 orbital. 2s contains 1 orbital. So, one orbital will take. We want one more orbital that we will take from 2p. So take one orbital from 2p. So one 2p orbital we have taken. So one 2s orbital we have taken, one 2p orbital we have taken. These two orbitals undergoing intermixing. These two on intermixing, we are getting two hybrid orbitals. We are getting two hybrid orbitals. So we got a hybrid orbitals. The hybrid orbitals having what nature means sp nature. It is sp hybrid orbital. This is another sp hybrid orbital. Therefore, these two atomic orbitals on intermixing we got two hybrid orbitals. These two hybrid orbitals have same energy, same shape, same shape. So these two hybrid orbitals are equivalent. These two hybrid orbitals are equivalent. Now, these two hybrid orbitals will take. In these two hybrid orbitals, how to fill the electrons in the sense as per Hund's rule, as per Pauli's principle. Now, the valence shell of beryllium is having 2 electrons. That 2 electrons we will fill in hybrid orbitals 1 year, another 1 year. As per Hund's rule, we have filled the electrons. Sorry. Now, these two hybrid orbitals orient around the nucleus of beryllium in which repulsion will be minimum, stability will be maximum. Now, it is a nucleus of beryllium. One hybrid orbital is orienting like this. It is one hybrid orbital. One hybrid orbital means one lobe is big, one lobe is small, center nucleus. It is one hybrid orbital. This hybrid orbital name is sp. This hybrid orbital contains one electron, that is unpaired electron. Another sp hybrid orbital, we will write another sp hybrid orbital, small lobe and big lobe. Small lobe and big lobe we have written. It is another sp hybrid orbital. It is having one electron, unpaired electron. Now, two hybrid orbitals of beryllium orienting to 180° in which repulsion is minimum, stability is maximum. Now, two hybrid orbitals of beryllium orienting linearly. Therefore, the angle is 180°. Angle is 180°. Now, repulsion between these two is minimum, stability is maximum. Okay. Next, we will take surrounding atom chlorine. For chlorine, we will take 3pz atomic orbital which contains unpaired electron. 3pz atomic orbital. Chlorine, 3pz atomic orbital contains one unpaired electron. Another chlorine we will take that also contains 3pz atomic orbital, that is nucleus, 3pz atomic orbital. This has one electron. Okay. So like this we have taken for this. Next, what happens means this sp hybrid orbital and this p orbital undergo linear overlapping, that is axial overlapping, that is overlapping along internuclear axis. Now these two orbitals overlapping, that is now that overlapping we will see it is a nucleus of beryllium. This is one sp orbital of beryllium. Next, p orbital of Cl is overlapping with this. This is p orbital, 3pz orbital of Cl. It is sp orbital of beryllium. These two overlapping, that means the two unpaired electrons becomes paired and bonding pair. Okay. Next, this sp orbital of beryllium and this 3pz orbital of chlorine undergo overlapping this side. So this is small lobe, and it is big lobe. Then it is sp orbital of beryllium, then 3pz orbital of chlorine. This is 3pz orbital of chlorine. Okay, overlapping. Then two electrons present here. Okay, so like this overlapping possible. Now here it is a nucleus of beryllium, here a nucleus of chlorine. Here we can say nucleus of chlorine, we can say. Now this beryllium sp orbital, chlorine pz 3p orbital overlapping to give sigma bond, overlapping to give sigma bond. In this sigma bond formation, beryllium sp orbital, chlorine p orbital overlapped. Then this side, this sp orbital, this 3pz orbital overlapping to give sigma bond, to give sigma bond. This sigma bond is formed by overlapping of beryllium sp orbital, p orbital of chlorine. Therefore we got beryllium chloride. Now you see this beryllium chloride, this is having two sigma bonds in its valence shell. One sigma bond nature is spp, another sigma bond nature is spp. Now this hybridization says that in the beryllium, the two bonds in the beryllium chloride, two bonds have same nature. So these two bonds have same nature, therefore these two bonds have same strength, therefore this bond length and this bond length will be equal. So experimental concept is explained by this hybridization. So what experimental concept says? This beryllium chloride has only one bond length, that is explained by this hybridization. Okay, so in beryllium chloride, the central atom beryllium is having what hybridization means? sp hybridization. sp hybridization we can say. Sir, next molecule we will take, next molecule is boron trifluoride. We will take boron trifluoride. We are taking boron trifluoride. In boron trifluoride, central atom is boron. For this atomic number is 5, electronic configuration is helium 2s2 2p1, 2s2 2p1. 2s contains one atomic orbital, 2p contains three atomic orbitals, 2p contains three atomic orbitals we can give. So for boron we have written like this. As per valence shell electron, as per valence shell electron pair repulsion theory, boron trifluoride structure is given as trigonal pyramid. Sorry, trigonal planar. Boron trifluoride structure is given trigonal planar. So boron is having three sigma bonds. Boron is having three sigma bonds. So three sigma bonds means we want three hybrid orbitals. Okay, so boron will provide three hybrid orbitals. To get three hybrid orbitals, boron will provide three atomic orbitals from its valence shell for intermixing. Okay, so how many sigma bonds are there? Count it. That many atomic orbitals you take from central atom in its valence shell for intermixing. Okay, so boron is having three sigma bonds. So from boron valence shell, how many atomic orbitals we have to take for intermixing? Three. Okay, take three. So this is the valence shell. 2s2 2p1 is the valence shell. In this valence shell, we have to take three atomic orbitals. How to take atomic orbitals? Least energy orbital you take first. What is the least energy? 2s is the least energy. Then if you want remaining, then next go for higher energy orbitals. Okay, so from this valence shell we will take 2s orbital, we will take. So one 2s orbital we are taking. We need totally three atomic orbitals for intermixing. Okay, one orbital is 2s, remaining 2v1, that you take from 2p. So two 2p atomic orbitals we are taking. Two 2p atomic orbitals we are taking. These three orbitals are going for intermixing. These three atomic orbitals are going for intermixing. Therefore, we are getting what in the sense hybrid orbitals we are getting. We are getting a hybrid orbitals. How many hybrid orbitals we got in the sense three hybrid orbitals we got. Three hybrid orbitals we got. That three hybrid orbitals, what is the name means? sp2 hybrid orbitals. The hybrid orbital name is sp2. Why? Because one s orbital and two p orbitals. This sp2 orbital is having what nature? What nature in the sense in this sp3 orbital 33% s character is there, 67% p character is there. this sp2 orbital is having 33% s character, 67% p character is present. Okay, so now these three sp2 hybrid orbitals have same energy, same shape. So we have to fill the electrons in these hybrid orbitals as per Hund's rule. This valence shell is having 3 electrons. That 3 electrons you fill in these hybrid orbitals as per Hund's rule. Therefore, 1 electron each for hybrid orbital. Okay. Now, these 3 hybrid orbitals orient around the nucleus of this boron. These 3 hybrid orbitals will orient around the nucleus of boron now. Okay. That orientation will give. Now, one hybrid orbital we have given like this. Here nucleus. Second hybrid orbital we have given here. Third hybrid orbital we are giving here. Third hybrid orbital we have given here. Okay. So 3 hybrid orbitals of boron is orienting around its nucleus with to the shape of a trigonal planar with the angle 120 degree. Okay. Now these 3 electrons we will write here. 1, 2, 3. These 3 electrons we have written. Next, surrounding atom is fluorine. In fluorine, valence shell is 2s2 2p 2p5. In that unpaired electron present in 2pz orbital, that orbital will take. So fluorine 2pz orbital contains 1 electron. Fluorine 2pz orbital for that nucleus is here. So another 2pz orbital for fluorine. So fluorine 2pz orbital contains 1 electron, here nucleus. So this is fluorine. This fluorine 2pz orbital contains 1 electron, that nucleus here. Okay. So this is boron. So boron 3 sp2 hybrid orbitals. For boron 3 sp2 hybrid orbitals. Fluorine we have written. Now boron sp2 orbital and fluorine 2pz orbital undergo overlapping. Okay. So boron we are writing. So boron sp2 orbital. Boron sp2 orbital. Fluorine p orbital. Fluorine p orbital. Okay. Now the bonding electrons will give in the overlapping part. Next, boron sp2 orbital, boron sp2 orbital, fluorine 2p orbital, fluorine 2p orbital. The bonding electrons will give here. Here, boron sp2 orbital and fluorine 2p orbital. Fluorine 2p orbital, the bonding electrons we are giving here. Okay. So this is boron, this is fluorine, this is fluorine, it is fluorine. So we will give boron 3 fluorine atoms. The bonding we have to give here 1 sigma bond. Similarly, here 1 sigma bond, here 1 sigma bond. This sigma bond is formed by overlapping between boron sp2 orbital and fluorine p orbital. Similarly, this sigma bond, this sigma bond. All the sigma bonds have same nature. Okay. This shape is what in the sense trigonal planar. Bond angle is 120 degree. All the bonds have same nature. All the bonds have same strength. All the bonds have same bond length. Therefore, BF3 has only one bond length. Okay. So in BF3, central atom boron is having what hybridization means? sp2 hybridization. So next we will take methane. We will take. For methane, central atom is carbon. Its atomic number is 6. Its electronic configuration is helium 2s2 2p2. Helium 2s2 2p2. 2s is having 1 orbital. 2p is having 3 orbitals. Okay. So methane structure we will draw as per valency shell electron pair repulsion theory. Methane one bond here, second bond, third bond, fourth bond. In methane, central atom carbon is having 4 sigma bonds like this. So carbon is having 4 sigma bonds. Therefore, from valence shell of carbon, 4 atomic orbitals undergo intermixing. So one atomic orbital is 2s. One atomic orbital is 2s and 3 atomic orbitals of 2p. 3 atomic orbitals of 2p. So 3 2p orbitals. So one 2s orbital, three 2p orbitals undergo intermixing. So these four atomic orbitals on intermixing, we are getting a four hybrid orbitals. The hybrid orbital name is sp3. Why sp3? In the sense, one is s orbital, three p orbitals, therefore sp3 hybridization. So all the hybrid orbitals name is what? In the sense, sp3. Now what is the percentage of s and p character in sp3? S is having 25%, S character is 25%, P character is 75% in each sp3 hybrid orbital. So each sp3 hybrid orbital has 25% S character and 75% P character is there. So now these four sp3 hybrid orbitals orient around the nucleus of carbon to tetrahedron. Now, so how tetrahedron will be there? We'll see. It is a nucleus. Now one sp3 hybrid orbital is orienting like this. Second sp3 hybrid orbital is orienting like this. Second sp3 hybrid orbital is orienting like this. Third sp3 hybrid orbital is orienting like this. Fourth sp3 hybrid orbital is orienting like this. Okay. All these three sp3 hybrid orbitals have same energy, same shape. So all the four sp3 hybrid orbitals are equivalent. So distribute valence shell electrons equally into all the four hybrid orbitals as per Hund's rule. So singly filled with parallel spins. Sir, how this tetrahedron is there means two hybrid orbitals will be in one plane. One hybrid orbital will be away from the plane, that means rear to the plane. Another hybrid orbital will be front to the plane. Suppose these two hybrid orbitals are in a plane of this screen. Then this orbital is rear of this plane. This orbital is closer to us. This orbital is closer to us. Like this we have to consider. Okay. So next we have to consider hydrogen atom. Hydrogen atom 1s orbital will take. Hydrogen atom 1s orbital contains one electron. So four hydrogen atoms. So four 1s atomic orbitals. Four 1s atomic orbitals we can write. So four 1s atomic orbitals we are writing. Okay. So four 1s atomic orbitals. Sorry. So in methane, central atom is carbon. Carbon is having four sp3 hybrid orbitals and four 1s orbitals of hydrogen. Now they are going for overlapping. Now it is a nucleus. One hybrid orbital sp3 and s orbital here. Next, in this overlapping part, we have to give two electrons. Bonding electrons, two electrons will give. Next, it is a second sp3 hybrid orbital. Here, 1s orbital of hydrogen, bonding electrons. Third sp3 hybrid orbital of carbon, 1s orbital of hydrogen, and bonding electrons we are given. Fourth sp3 hybrid orbital and 1s orbital, then bonding electrons. Okay. So this is carbon, these are hydrogens. Okay. In this, two bonds will be in one plane. So carbon, two bonds will be in one plane. Suppose these two bonds is in the plane of this screen. Now this hydrogen is rear of this screen. Okay, rear of this screen. This hydrogen is present rear of this screen. Then this hydrogen is present front to the screen. That means closer to us. Okay, this hydrogen present closer to us. This is what in the sense tetrahedron. Tetrahedron in the sense if you join any three hydrogen atoms, you join here, you will get a equilateral triangle. And how many equilateral triangles you will get? In the sense, four equilateral triangles you will get, therefore tetrahedron. And what is the bond angle means 109 degree 28 minutes for this. Okay, then this bond is called sigma bond. This sigma bond is formed by sp3 orbital of carbon sp3 orbital of carbon and s orbital of hydrogen. Therefore, this sigma bond is sigma sp3s. In the same way, other three sigma bonds also, all the sigma bonds will have same nature. Therefore, all the sigma bonds will have same strength. So all the sigma bonds are having same bond length. So this molecule is having only one bond length. This shape is tetrahedral. Bond angle is 109 degree, 28 minutes. Okay. Next, we will take a PCl5 molecule. We will take. In PCl5 molecule, central atom is phosphorus. Atomic number of phosphorus is 15. Its electronic configuration is neon 3s2 3p3 3p3 3d0. Okay, so 3s is having one orbital, 3p is having three orbitals, 3d is having five orbitals. 3d is having five orbitals. Okay. Now, as per valence shell electron pair repulsion theory, what is the structure of PCl5 that we will see? Structure of PCl5 as per valence shell electron pair repulsion theory that we are seeing. So PCl5 will write here 1 Cl, here 2 Cl, here 1 Cl, here 1 Cl. That means phosphorus has 5 sigma bonds. So from the valence shell of phosphorus, 5 atomic orbitals undergo intermixing. 1 3s orbital, 3 3p atomic orbitals, 3 3p atomic orbitals. So totally how many means 4? So 1 3d orbital, 1 3d orbital undergo intermixing. So these orbitals are undergoing intermixing, we can say. So on intermixing, we are getting how many hybrid orbitals means how many orbitals undergoing intermixing, that many hybrid orbitals we will get. Therefore, we will get 5 hybrid orbitals we are getting. We are getting 5 hybrid orbitals we are getting. That 5 hybrid orbitals in the sense, what is the name in the sense sp3d. sp3d is the hybrid orbital name. One orbital is s, 3 orbitals p, 1 d orbital. Therefore, sp3 hybridization. Okay. How many hybrid orbitals in the sense 5? Okay. It is a nucleus of phosphorus. 1 sp3 hybrid orbital, 1 sp3 hybrid orbital we will write here 1 sp3 hybrid orbital, another sp3 hybrid orbital, next sp3 hybrid orbital. This is a top one hybrid orbital, this is a down one hybrid orbital. 5 hybrid orbitals we have given. Each hybrid orbital has one electron. Each hybrid orbital has one electron. Valence shell contains 5 electrons for phosphorus. Those 5 electrons we have distributed equally into all the hybrid orbitals. Now, surrounding atom is chlorine. For chlorine, 3pz atomic orbital we have to take. Okay, chlorine 3pz atomic orbital. Chlorine 3pz atomic orbital we are taking. So for chlorine, we are giving 3pz atomic orbital. So how many chlorine atoms means 5 chlorine atoms. So 3pz atomic orbitals we are given here. Okay. So each 3pz atomic orbital of chlorine has one electron, has one unpaired electron. Okay. Now here this sp3d hybrid orbital and this 3pz orbital undergo axial overlapping. So it is the phosphorus nucleus. It is one hybrid orbital of phosphorus and it is a 3pz orbital of chlorine. Undergo overlapping. Here bonding electrons we will write. Then next we will write this is sp3d and this is 3p of chlorine. Here bonding electrons. Next sp3d of phosphorus, sp3d of phosphorus and 3pz of chlorine, bonding electrons. Next here sp3d of phosphorus and 3p of chlorine. Next orbital sp3d of phosphorus and 3pz of chlorine. Here bonding electrons we have given here. Okay. So we are getting PCl5. In PCl5, one bond is here, second bond, third bond, fourth bond, fifth bond. Like this we have given. Here, if we join these three chlorine atoms, you will get a triangular shape. Trigonal planar we will get. This Cl is down, this Cl is up. This up Cl is called axial Cl. This down Cl also axial. This is equatorial. This is what in the sense equatorial we can say. Equatorial Cl we can say. Here what is the angle in the sense 120 degree. Here what is the angle in the sense 90 degree. Now this is sigma bond. This sigma bond is formed by sp3d of phosphorus and p orbital of chlorine. See this sigma bond also same. This sigma bond also same like this. This sigma bond also formed by sp3d of phosphorus and p orbital of chlorine we can say. So all the orbitals have same nature, that is all the orbitals are formed by overlapping of sp3d and p orbital. But bond length is different. What is the bond length different in the sense this equatorial bond length and axial bond length are different. Why? Because between equatorial bonds angle is 120 degree, between axial bond and equatorial bond angle is 90 degree. Since angle between axial and equatorial is less, this axial chlorine is lengthening. Lengthening means it is going far away from phosphorus. Therefore, this bond length will be high and this bond length will be low. So that here two types of bond lengths are there. Bond length of PCl axial is greater than bond length of PCl equatorial. Like this will be there. Bond length will be like this for PCl5. So in PCl5 central atom phosphorus hybridization is what in the sense sp3d hybridization. Okay. Next we will take SF6. In SF6 we can write sulfur atomic number 16. Electronic configuration is what means neon 3s2, 3p4, 3d is 0. 3d is 0. 3s contains one atomic orbital. 3p contains three atomic orbitals. 3d contains five atomic orbitals. Okay. So SF6 we can write like this. As per valence shell electron pair repulsion theory, SF6 is having octahedral shape. Octahedral shape. This sulfur is having uh, six bonds. Therefore, from the valence shell of sulfur, one 3s orbital, one 3s orbital, three 3p orbitals, three 3p orbitals, and two 3d orbitals. Two 3d orbitals undergo intermixing. Undergo intermixing. Therefore, we are getting a six hybrid orbitals. We are getting. We are getting six hybrid orbitals. Six hybrid orbitals we are getting. The name of hybrid orbital is sp3d2. sp3d2 is the name of this hybrid orbital. Sir, okay. Now that six sp3d2 hybrid orbitals orient in what manner means in a octahedral manner. Orient in octahedral manner. Okay. So it is the nucleus. One hybrid orbital will write like this. Second hybrid orbital will write like this. Third hybrid orbital we are writing. Fourth hybrid orbital we are writing. Then fifth hybrid orbital, sixth hybrid orbital. Okay, six hybrid orbitals we have written like a octahedral manner. Okay, these four if you connect, you will get a square planar. This is up and this is down. Like this is there. And the fluorine 2pz atomic orbital we have to write. So for fluorine 2pz atomic orbital. For fluorine we are writing a 2pz atomic orbital we are writing. For fluorine 2pz atomic orbital. So it is what means sp3d2 and it is 2pz. They are undergoing overlapping. Therefore, we are getting a sf6 like this. In this sf6, we can say this is sigma bond. This sigma bond is formed by overlapping of sp3d2 of sp3d2 of sulfur and p orbital of fluorine. All the sigma bonds have same nature, same strength, same bond length. So in SF6 bond length will be only one. Here we cannot say axial, equatorial and all. We cannot say bond angle is everywhere. If you see bond angle is 90 degree. It is a octahedron. Why? Because if you join three fluorine atoms, neighboring three fluorine atoms, if you join, you will get equilateral triangle. How many equilateral triangles we will get? In the sense, 8 equivalent equilateral triangles we will get. Therefore, it is a octahedron, we can say. If you join these four fluorine atoms, you will get a square planar. This fluorine will be down of that plane. This fluorine will be above of that plane. Like this will be there. Okay. Next molecule is what? In the sense, IF7. IF7 will take. In this IF7, in the sense I we will write, and 7 fluorine atoms we will write. It is 1, it is second, it is third, it is fourth, it is fifth, it is sixth, it is seventh. So 5 fluorine atoms we have written. Now we will write the bonds. Here, these 5 bonds, these 5 fluorine atoms will join. We will get what? In the sense, pentagon we will get. Pentagon, this fluorine is above the pentagon, this fluorine is down the pentagon, like this is there. In this iodine, how many bonds are there? Means 7 sigma bonds are there. 7 sigma bonds means, how to split 7 means, first one you give to S, because S orbital will have 1. Then you give to P. P means 3 orbitals, so give P. Then you take D. D in the sense, how many? In the sense, first you add up these 3, these 2 you add up, this 1 plus 3, 4, this 4 you subtract here. So what is the remaining? In the sense 3, that 3 you give here. Therefore, what is the hybridization of iodine? In the sense, sp3d3 hybridization. So how to find hybridization, that we'll see. Okay, how to find hybridization? First we will take a beryllium chloride. Beryllium chloride is like this. Here, beryllium chloride is having 2 bonds. In beryllium, 2 bonds are there. In 2 bonds, first you write S, P, D, you write like this. Okay, first you give for S. S in the sense only 1 orbital, so we can give for S only 1 only. So here how much is there? See, total 2. In the 2, 1 we have given. Remaining 1 is there, that you give for P. Then you cancel D, because P itself not completely completed. Therefore, you cancel D. So what is the hybridization of beryllium in beryllium chloride? Means sp hybridization. So then we will take BF3. BF3 we have written like this. In this boron, 3 bonds are there, 3 sigma bonds are there. So you write SPD, you write it. In that 3, first you give 1 to S. S in the sense only 1 orbital. Then remaining you give to P. Okay, so P is maximum, P is 3, but here only 2 is there, therefore D is not there. So what is the hybridization of boron in BF3? Means sp2 hybridization. Then we will take methane. Methane, CH4. CH4 we have written. This carbon is having 4 sigma bonds. 4 sigma bonds. Now you write S orbital, P orbital, D orbital. In that, for first you give 1 to S. S means only 1 orbital. Then remaining how much? 3. So 3 you give to P. P subshell contains 3 orbitals, so we have given 3 orbitals. 1 plus 3, 4. So totally 4 is over. Therefore, D is not there. So what is hybridization of carbon here? sp3 hybridization. Then we will take PCl5. PCl5 we can write a trigonal bipyramid, that we have written. Phosphorus is having 5 sigma bonds. 5 sigma bonds we have written. So you write SPD, you write. In that 5, first you give 1 to S. S is having only 1 orbital. Then you give 3 for P. P subshell is having 3 orbitals. So total how much? 4. But how much is there? 5. So remaining how much? 1. That you give to D. So sp3d is the hybridization of phosphorus in PCl5. Next, we will take SF6. SF6 means sulfur and 6 fluorine atoms. 6 fluorine atoms we will write like this. 6 fluorine atoms we are written like this. Sulfur is having 6 bonds. And that 6 bonds, how to give? In the sense, sp, do you write it? In that 6, first you give 1, remaining is 5. Then go to P. P can, for P you give 3, remaining is 2. That 2 you give to this D. So hybridization of sulfur is sp3 D2. So IF7 will see. In the IF7, I is having 7 fluorine atoms. I is bonded with 7 fluorine atoms like this. Trigonal, this is pentagonal bipyramid. Here 7 sigma bonds are there. 7 sigma bonds. You write S, P and D. In that 7, 1 you give to S, 3 you give to P, and remaining how much? Means 3. That 3 you give to D. So what is the hybridization of iodine in IF7? Means sp3d3 hybridization. So like this we have to say hybridization, we have to say. Okay, if we have seen only sigma bonds we have seen. So far we have taken the molecules in which only sigma bonds present. Now we will go for the molecule in which a central atom is having even lone pair cell. Now how to say hybridization, that we'll see. Even lone pair will be there, that such a type of molecules will take. Now we will take ammonia. In ammonia, central atom is nitrogen. Nitrogen electronic configuration is helium 2s2 2p3. 2s is having one atomic orbital, 2p is having three atomic orbitals. Set. So now we will see ammonia structure as per valence shell electron pair repulsion theory. Ammonia structure is this one. Ammonia structure is this one. In that central atom is nitrogen. Nitrogen valence shell has 5 electrons because it is coming under 5th A group. So 5 electrons we can write here. 1 electron, second electron, third electron, fourth electron, fifth electron. So this is what in the sense lone pair. Okay. So nitrogen valence shell. Nitrogen is having three sigma bond pairs, and one lone pair. That means totally how much? Means totally 4 electron pairs. Therefore, nitrogen should provide 4 hybrid orbitals. Okay, one hybrid orbital for lone pair, 3 hybrid orbitals for forming these 3 bonds. Okay, so nitrogen should provide 4 hybrid orbitals. Therefore, nitrogen is providing 4 atomic orbitals from its valence shell for intermixing. One atomic orbital from 2s, one atomic orbital from 2s, and 3 2p atomic orbitals, and 3 2p atomic orbitals. So totally 4 atomic orbitals undergoing intermixing. 4 atomic orbitals undergoing intermixing. Therefore, we are getting 4 hybrid orbitals. We are getting 4 hybrid orbitals. These 4 hybrid orbitals name is sp3 hybrid orbitals. These 4 hybrid orbitals are called sp3 hybrid orbitals. Okay, now we will consider it is a nucleus of nitrogen. It is a one sp3 hybrid orbital. This is a second sp3 hybrid orbital. Then it is third sp3 hybrid orbital. This is a fourth sp3 hybrid orbital. Okay, this hybrid orbital name is what in the sense sp3. Then how to fill the electrons? How to fill the electrons in these hybrid orbitals? We have to see. Now you have to fill such that for lone pair. Okay, so for one lone pair, therefore for one hybrid orbital you give 2 electrons. For one hybrid orbital you have to give 2 electrons because nitrogen valence shell is having one lone pair. Nitrogen valence shell is having one lone pair. Therefore, for one hybrid orbital, you give pair of electrons. For one hybrid orbital, you have to give pair of electrons. You have to give then 3 bond pairs. Therefore, for 3 hybrid orbitals, you give 1 electron each. For 3 hybrid orbitals, you are giving 1 electron each. Okay. So 3 bond pairs. Therefore, for 3 hybrid orbitals, you are giving 1 electron each. One lone pair. So for one hybrid orbital you are giving pair of electrons you are giving. Okay, then hydrogen you have to take. Hydrogen is 1s1 electronic configuration. Hydrogen is having one electron in its 1s orbital. Hydrogen is having 1s orbital, 1 electron. Now what happens means here overlapping is possible. So that overlapping will give, that overlapping we are giving, it is a nucleus of nitrogen. It is a one hybrid orbital. This hybrid orbital contains pair of electrons. Next we will take hybrid orbital. This hybrid orbital is overlapping with a 1s orbital and it is having 2 electrons, we can say. This is a next hybrid orbital. It is overlapping with the 1s orbital, 1s orbital like this. Next we will take hybrid orbital. This is a overlapping with a 1s orbital, that pair of electrons. Okay, so here central atom nitrogen, it is bonded with 3 hydrogen atoms, we can say, and this lone pair we can give. This is what means lone pair. This lone pair present in what orbital means sp3 hybrid orbital. This is sigma bond. This sigma bond is formed by overlapping of sp3 of nitrogen and s orbital of hydrogen. This is sigma bond. This sigma bond is formed by overlapping of sp3 orbital of nitrogen and s orbital of hydrogen. These 3 sigma bonds have same nature. Therefore, these 3 sigma bonds have same strength. So only